Alrighty, so for today's lesson, what we're going to talk about is the other 2 points of concurrency. We've already discussed the orthocenter and the incenter. Today we're going to be doing 2 other ones. So perpendicular bisectors, I think that you know already. A perpendicular bisector is a line segment that passes through the midpoint of the opposite side, and it's also going to be perpendicular to that side. So if you take a look, that all of these pieces right here are midpoints because you can see the markings as such. So we've got midpoint, 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 and then when we actually go through that midpoint and make a right angle, we've now created perpendicular bisectors. Well, all of those perpendicular bisectors meet at a point of concurrency. That's that point right there, and that point of concurrency is called the circumcenter. So the 3 perpendicular bisectors of any triangle meet at the point called the circumcenter. And what's special about the circumcenter is that if we were to draw a line segment from the circumcenter to each vertex of the triangle, circumcenter to A, circumcenter to B, and circumcenter to C, those segments would all be congruent. So that's the only thing that's really special about the circumcenter. Let me just kind of show you the sketch pad real fast. So in Sketchpad, what happens here is we've got these perpendicular bisectors. Notice how all of these values are going from circumcenter to vertex A, circumcenter to vertex B, and circumcenter to vertex C. You don't see those things shown. You're only seeing the actual perpendicular bisectors being shown right now. Okay. What's happening is I could always sit here and I can actually create this. Will it let me construct this line segment? So there it is. Construct this line segment. Construct this line segment, construct it, try that one again, hold on. Construct this line segment. And what I'm going to do is I'm going to hide the perpendicular bisectors. So all now that you're seeing is the circumcenter to all those vertices. As we look on the side and we drag this triangle, those values constantly stay the same. Doesn't matter what the triangle looks like, but as long as I've got the circumcenter to all the different vertices, I'm always going to have equal segments. Okay, so from the circumcenter to the vertices. Alrighty, so there's that. No. Okay, so the next one that we had talked about is called the medians. And median, by definition, I think you know this too, is a line is a line segment drawn from any vertex to the midpoint of the opposite side. So the 3 medians are all going to meet at a point, and that point of concurrency is called the centroid. This is the one that has the most useful, not really useful, but the most, I guess, important information that's about the centroid. The centroid divides each median into 2 parts so that the distance from the centroid to the vertex, this distance right here, is twice the distance from the centroid to the midpoint of the opposite side. So basically we have a ratio. We've got a 1 to 2 ratio. So you can basically think of dividing that median into 3 equal parts, and then twice those parts happens to be the longer piece or centroid to vertex, and then the other part happens to be from the vertex to the median. The other thing about the centroid is that the centroid happens to also be known as the center of gravity. And I'm going to hope to, in class, actually let you guys take a look at some triangles of different sizes and take their centroids. And you should be able to hold that triangle by your fingertip on that centroid, and that triangle should be perfectly balanced. So we're going to try that in class. But I want to show you something about the ratio of those medians. So let's go to the sketch pad again. So what's happening now is we know that we've got these medians drawn in. Okay, just the medians, it tells you that here. If you look at from the vertex, I'm only showing you one median that's measured. If I look at this one along this line right here, maybe what I can do, can I hide these? No. Okay, that's okay. So If you take a look at this particular median from A to J, you'll notice that from A to CE is 4.04, and then from CE, centroid, to J is 2.02. Notice how the bigger part is double the smaller part. You could drag this triangle, whoopsie, maybe not that way, maybe not that way. As you drag the triangle however you want, you should notice now this is rounded, but that the longer part is going to be double the smaller part. If I can get you some even numbers, that might be better. Like this one, 2.92 doubled is 5.84. So again, the smaller part is here. If I double the smaller 2.92, there's the larger. Okay, and so that happens every time you deal with the centroid when you create all the medians together. All right, let's do some work with this then. Alrighty. So here in this case, what's happening is they tell you that PL is 24. They tell you that QC is 10 and KC is 7. They want you to find PC, CL, QM, and CR. So one of the first things that I would probably take a look at is the fact that I've got PL. This whole thing is 24. Well, remember, if I cut 24 into 3 equal parts, I can see that each third is 8, which means my smaller part, in this case, is CL, and then my larger part is double the smaller, and this is PC. So that's what happens here. PC is 16, CL happens to be 8. Take the entire thing, cut it into 3 because it's a 1-to-2 ratio. If I take a look at QM, okay, so QM, they're telling me that QC right now happens to be 10. Well, that's the bigger part. That's the double part. If QC is 10, then CM is 5, and all of QM is 15. If I take a look at the given of KC, KC is the smaller part. KC is 7, which means CR happens to be 14. And that would be the end of this particular question. Okay, take a look at the next one. S is the centroid. All the measures are in centimeters. So you know that SP happens to be 6. Okay, so if SP is 6, then you know that SR is 12. This is double. Well, SM is SR plus 6. So SM happens to be 12 plus 6, or SM equals 18. Then it wants you, I guess in this case, let me go over here. SM then is 18. So if SM is 18, that's 2. That's twice what the smaller part HS is, which means if you cut that in half, HS ends up being 9. Okay, let's try this next one. You've got all the medians and they intersect at P, so P is your centroid. If BE, if this whole thing is 3x, and then it tells you that BP, the bigger part, is 8x minus 12. Well, you want to find some other values. You can do this a couple of ways. One of the things that I think might be helpful is you know, or you should know, that all of BE is equal to whatever BP is plus PE. Okay, so we can also say that you know PE, the smaller part, is half of BP. This is the first way that I'm going to do this. I'm going to find out what PE is. So PE equals 1/2 of 8x minus 12, which means PE equals 4x minus 6. So now I know that this bottom is 4x minus 6. At this point, you might as well just set up an equation that says, well, my whole thing is equal to my smaller part plus my larger part. So that means 3x, whoopsie, not 36. 3x equals, combine like terms, 12x minus 18. When I solve this equation, I subtract 12x on both sides. You're then going to get 9x or negative 9x equals negative 18. So x equals 2. So how does that help us? Let's see. It wants you to find BE. Well, if I plug in 2 for BE, I guess I'm going to kind of go over here. BE, when I plug in 2 here, I get 6. BP, when I plug in 2 here and I do the math, 8 times 2 is 16. 16 minus 12 is 4. And then I could actually just go right from there and say, well, if the bigger part here is 4, then this guy has to be 2. So PE equals 2. And there's your answer. Now that's just one way of many ways to do it. So you can kind of decide how you want to do it, but that's one way that I think hopefully makes sense. Okay? So good luck on the homework.